Hello, this is Rob, and I thought since I was gone, I would give you a quick overview of section 5.3. I know Chris McClure is doing a great job, but I thought I would send out a video just so that you felt that I didn't abandon you. Please email me with any questions that you may have. So in section 5.3, I've already taught a lot of this, exponential and log integration. This is the definition that we used in class, the definition of e to the u du. I'm saying e to the yellow, d yellow, if you remember. I'll go over that in a moment. Here's a couple examples that Chris hopefully went over. This one, we're going to use our constant rule, so I can just bring the constant straight out front, one of the integration rules. So this is really just 2 times the integral of e to the x. And of course, the derivative of the derivative of e to the x is e to the x, and therefore the integral of e to the x is also e to the x. So a is not very difficult to do. Don't forget, when you take the integral, you also need to remember that there could be a constant, because when you take the derivative of 2e to the x plus 6, the 6 will go away, or the 7 will go away. So there's always some kind of a constant. Let's take a look at, there's the answer for A. So we'll take a look at part B. And in part B, you might want to think about throwing the 2 out front, but in this case, look at the u du. If you do a quick u substitution and let u be 2x, then notice that my du has a 2 in it. So my recommendation this time would not be to throw the 2 out, because we're actually going to use this 2 right here in blue as part of our du, because the derivative of du is 2 dx. And you always need this dx because you're implicitly taking the derivative of u, so I'll write dx here. So if I were to solve for dx by dividing both sides by 2, I get a new rule, and the rule says replace dx with du divided by 2. And so notice, if you do that, I'll get the integral of 2e to the 2x, and then I'm going to replace this integral du divided by 2 with this dx, because that's what dx is equal to. So instead of writing dx here, I'll write the value, which is du divided by 2, and nicely enough, we can cancel the 2's. So if you would have had the 2 out front, we wouldn't be able to do that. So this one, we get the integral of e to the 2x. But remember, you're replacing 2x with your u substitution. So I'll say e to the u, and then, of course, we have our du, which is still hanging around. So I've replaced all of my x's, it's called a u substitution, with u's. And of course, we know e to the u, the derivative, or excuse me, the integral of e to the u is simply just e to the u. So my final step would be to replace u back with the substitution that I've made before, and u is 2x, and then we'll say plus c. So my final solution is e to the 2x plus c. For our third example, I notice that we have a sum, and the integral of a plus b is really the integral of a plus the integral of b. And so I'll really try to make 2 problems out of this one. Try to do that every time you see a sum. It's easier to break it up. So the integral of e to the x is e to the x. And the integral of x to the first says we're going to increase this 1 by 1. That's what integration means. We increase by 1, so the 1 goes to a 2. And then we'll divide by that 2. And then lastly, we'll say plus c, plus some constant. If you wanted to find a common denominator, you could. It's the same solution, but I honestly would probably just stop right here like the author did. For our second example, again, let's try a u substitution. The u substitution says, because the only thing we know is the integral of e to the u is e to the u du. And I don't have e to the u. I've got a funky looking u here. So I'll say u is equal to 3x plus 1. So therefore, the derivative du is equal to just 3. Well, it's 3 dx, and I notice over here, well, I don't have a 3 dx. So I'm going to have to replace, when I do my u substitution, I'll have to replace dx with what dx is equal to. So if you divide both sides by 3, we have a nice equation over here. Our new dx will be, in terms of u, du divided by 3. So I'm going to rewrite all of these x's in terms of my u substitutions. Once again, I'll get the integral of e. I've replaced the yellow with my u substitution, and I've replaced dx with du divided by 3. And of course, divide by 3 means you pull out a constant 1/3. And so now I'm looking at the integral of e to the u du. And I know the integral of e to the u is e to the u. But I'm going to replace u back with the value of u, which is the 3x plus 1. And lastly, plus c. And it looks like, good, the author is leaving it in this form as well. I don't know what other form you could leave it in, possibly. For this one, again, I see a constant. I don't know if I'm going to pop that 5 out or use the 5, but it doesn't look like my u substitution is going to need the 5. You might find that you might want to put the 5 back in. But looking at the du and the u, it doesn't look like I'm going to be using that 5. I do think I need to create an x. And you can't pop out an x anyway, so I'm leaving this x in here. E to the negative x squared dx. So again, I always try to let u, and sometimes it's very tricky to try to figure out what to let u be, but I always try to let it be the inside function. In this case, I'm going to let u equal negative x squared. Maybe I should just let it be positive, but we'll try the negative. If it doesn't work, we'll go back and try something else. So if I do let u be the negative, I'll get the derivative to be negative 2x dx. And that's fine because I see that I have an x and a dx that I need to use. So this x and dx is part of my problem over here, which is good. But the 2 is not. So I'll probably divide off the negative 2 to both sides. And I'll get a nice little substitution that says replace x and dx, this whole product, with du divided by negative 2. So let's go see what our u substitution looks like now. It's the integral of course, remember, all of this blue gets replaced with this over here. So I'm just going to write down e to the, remember, the yellow was my u substitution, so e to the u. And all of this goes to, well, not du, but in this case, du divided by negative 2. And I can pull out the negative 2. And let's make this a negative 5/2. The integral of e to the u du. And of course, the integral of e to the u is e to the u, but I'm going to replace u back with the u substitution, negative x squared plus c. And I'll tag on my negative 5/2. And yay, the author agrees again. That's nice when we get the answer in the back of the book. I haven't looked at this yet, so I'm glad we're doing pretty good. We'll keep moving on. Using the log rule, here comes, it's pretty much the same definition that we've been using here. If you integrate u to the n, you increase n by 1 and divide by it. And then the log rule says, but since you can't really do this, if you were to rewrite this to be the, and oh, there it is, the integral of x to the negative first, well, if you try to increase that negative 1 by 1, you get x to the 0, and that causes complications. So we come up with a log rule, and it says every time you integrate 1 over x, you get the natural log of x, or 1 over u du, you get the natural log of u for a u substitution. So let's see if we can try one. I see I have a constant, so I'll pull out the constant 4. This is the integral of then 1 over x, starting real easily. Using the definition, the integral of 1 over x is the natural log of x plus c. For our second problem, we'll see if the author agrees. Yep, use the absolute values for natural log of x. Good. Good. For our second problem, at first glance, it looks like we could pull out a 2, or maybe even though you cannot. It looks like you could maybe reduce this fraction, but because these are variables, that is dangerous to do. In integration, you actually have to not simplify. If you're going to cancel out fractions, it'll actually change the integration. So don't reduce this. And then I see if I try a u substitution, I might want to keep that 2 inside because I think I'm going to let u be x squared. If I do, then I'm left with du equaling 2x, which 2x dx, I see something coming together now. This 2x dx is all part of my du substitution. So I'm going to try to rewrite this in terms of u as 1 over x squared, and then all of this yellow becomes my, excuse me, it's not 1 over x squared. I replaced it. X squared with my u substitution. It's just 1 over u. And then the 2x dx just gets replaced with, sorry, it's late, with du. Oh, and that's very nice. The integral of 1 over u du is just the natural log of u. Now I'm going to replace u back with x squared and tag on a plus c. Boy, I botched that one, but hey, looks like we did pretty good. The ln of x squared plus c. So that one was tricky because, again, it was baiting you to reduce the fraction, and I would recommend you do not do that. For this last one, again, I'm trying for u substitution, looking for these log rules, which is 1 over u du. I'll let u be the denominator so I can try to get it into that form. So the hint is, whenever they say use these log rules, you probably want to end up with 1 over u du. So what happens when, again, you see that the derivative of this is 2 dx, but I don't have a 2 this time. So we're going to have to create, well, I do have a 2, but this is part of my u substitution. I don't have another 2 in the numerator, so I'll solve for dx by dividing by 2. So I'll replace dx right here. This yellow dx gets replaced with du divided by 2. And I think you've seen this before. You're getting more and more comfortable with this. So all of this is my u substitution. So I'm going to rewrite this as 1 over u. And then I replace dx, this yellow, with all of this yellow. Of course, it's du divided by 2, which I see a 1/2 in here. So I'll pull out 1/2, the integral of 1 over u du. And you're starting to realize after you do a couple of these that the integral of 1 over u is the natural log of u. And I'll replace u back with my u substitution. The 2x minus 1, and say plus c. And they have 3s. I had a 3. I didn't. Well, I went on to example 5. Okay, so sorry. Well, if you want to see example 3, it's worked similarly. It's just that they had a 3 up here. I could work this real quick. I'm so sorry. I didn't really realize I jumped onto 5. But this 3, this is similar. If I were to let u be the denominator here, this one's even a little bit easier because my u substitution is 3x plus 1. And then notice when you take the derivative of u, you get 3 dx. So I'm replacing all of this 3 dx with my du. So I have the integral of 1 over u. The author writes it a little bit funny, so that's why I wanted to do this video. So I would rewrite it 1 over u, and then all of this is my du. The integral of 1 over u is just the ln of u, and I'm going to replace u with the value, 3x plus 1, and say plus c. We get the same answer. It's just, yeah, I work it maybe just a little bit differently. So sorry, I'm trying to write this with my mouse so it comes out really like a 3-year-old is writing. But number 5, I think I worked it out. It was similar, but we were missing the 2. And yay, the author agrees with me. I'm looking down here. This is the answer that I got. The author works it just a little bit differently than I do, but again, the results are the same. For example number 6, I'll make a second video. If you're interested in continuing this, I have a couple more examples, and I'll make a second video and post that to YouTube as well. I hope this was helpful. Please give me a shout out, email me with questions. Thanks. Bye.